All right. Happy election day, everyone. How are you? Did you vote? Are you going to? If you haven't, go do it. It's California. You can even register today. If you're not registered to vote, go register and then vote. Your age group could completely control the country if you wanted to, because such small numbers of, 18 to 29s vote. If you all voted, you can have the country any way you want it. That's just kind of how it plays out. So go do that. Let's see. Last week we were talking about conservation of energy. We did a couple of examples. Let me just rehash a little of what we talked about. We're going to add to that today and work a couple more examples. So we were talking about this idea that you have a combination of kinetic and potential energy, and that stays constant throughout the course of the problem. So the sum of those at the start equals the sum of those at some later point in the problem. Kinetic energy at this point is all about velocity. If it's moving, it has kinetic energy. If it's not, it doesn't. Okay. Potential energy, on the other hand, we've got two different types we can deal with right now. If the object is not at y equals 0, if it's, say, off the ground, if it's above the ground, if it has height, then it has gravitational potential energy. If there's a spring involved and the spring is stretched or compressed, it's storing spring potential energy. So you'll have to look at the problem and see which one of those are applicable, and it could be both of them. So the idea is that there is a certain amount of energy in the system which could be represented by maybe a bucket that stores that energy, and the type of energy can change. So the amount that you have in there can move between kinetic and potential. But if you have a loss of one, it has to be represented by a gain in the other, and vice versa. Okay, it's changing types of energy, but you're not gaining or losing any. We're going to expand this idea in just a few slides today. So we're going to take that same concept and add a little something to it. So we worked an example with projectile motion, and I suggested that over the weekend you try it with kinematics as well. You all did that, right? Good job. A couple of you lied to me, that's fine. So go practice that. You'll need it for the final exam, all right? And we did another problem that involved a spring and gravitational potential energy, which brings me to this. I'll give you a chance to read it, and then we'll talk. So the situation looks something like that. You've got a skier at rest, so it has no kinetic energy at the top, skiing down a slope to the same final position. But you and your friend have chosen different locations for y equals 0. So maybe one of you decide it's there. Maybe one of you decides it's halfway down the slope. So if you just calculate m times g times y, clearly both of you are going to decide, well, there's different amounts of potential energy at different points along the slope. So you can't agree on that particular number. But if I just look at what the difference here is in positions between here and here, no matter what I call them, the difference is the same. You're going down the same amount, no matter what labels I give those numbers. So if I look at how much potential energy you have here and subtract it from down there, this becomes irrelevant. It just doesn't matter at all. So you're going to agree on how much the potential energy changes from top to bottom. And if all of that change in potential energy goes into kinetic energy, then you must be agreeing on how much kinetic energy you have at the bottom as well. Okay? So this points out the fact that y equals 0 doesn't matter. It's the change in potential energy and the fact that that affects how much kinetic energy you have that really matters. All right? Let's see. What about this? Two paths lead to the top of a big hill. One is steep and direct, and the other is twice as long but less steep. So maybe ground level is down here, and maybe, I don't know, the top of the hill is way up here somewhere. And one path goes like that, and the other path getting to the top of the hill goes like this. In which, or how much more potential energy would you gain if you take the longer path? Or does it matter? Keep in mind, you're going to the exact same Y final. This change in your vertical position is all that matters when it comes to potential energy. So you are going to, how much more potential energy would you gain? You would have the exact same amount of potential energy when you finish. Remember back with conservative forces, it didn't matter which path you take when you're dealing with a conservative force. We're dealing with gravity here. It's illustrating the fact that you're going to get the same amount of potential energy at the top, no matter which path you take. Even if you wanted to go, woo, and I don't know where that's happening, but you get the idea. All is going to be the same as long as you start and end at the exact same place. So this is asking a similar question. Read it and tell me what you think. One because it's the steepest. Okay, so we've got to vote for one. Anybody else want to add to one? Anybody want to add a vote for two? Anybody want to not vote? That could be a number 5 there. You're all like over here. That's all of you. Number 3? 4? Got a few for 4. We'll kind of, okay. Does anybody want to defend their answer? While I erase like all of these extra marks because that's just going to be confusing later.
I switched mine to 4.
You switch yours to 4. Does anybody want to defend the 4? Why 4?
So they all have the same potential when they start.
They all have the same potential energy when they start. So what does that mean?
So at the bottom of the ramp, they'll all have the same kinetic energy.
Yeah. When they get to the bottom of the ramp, thank you, they'll all have the same kinetic energy because that's just being converted from potential to kinetic. And if they have the same kinetic energy, they must have the same velocity. Here's the trick to this question. Do they all get to the ground level at the same time?
No.
They do not. Okay? This one is going to get there sooner because it has a shorter path, right? And it's also going to pick up its velocity faster. But it's not going to be going any faster when it gets to this bottom point than any of these others, all right? It's just that there's a sooner or quicker acceleration, okay? The entire thing just doesn't take as long to happen. So let's continue with this. Actually, I want to skip this problem except for pointing out the beautiful truck. Look at that. Compared to some of the other things that we've seen, I think they wasted all their time illustrating this truck and took no time on anything else. So that's very nice. It's beautiful. Thank you for all that work. We're not doing that problem, though. Instead, I want to get to this. We're going to add to the equation that we had before, except now we're going to include non-conservative forces, forces that just throw energy away. They waste the energy in some way. You might remember our example of a non-conservative force is friction. So we're going to start putting friction in the problems. And one way of thinking about what a non-conservative force does is by looking back at the energy bucket. So perhaps, again, we have a kinetic energy side and a potential energy side. And maybe we have some energy in both of these sides. Maybe different amounts, I don't know. However, I'm going to scare somebody. Hello. Sorry to be standing here when you walked in. That's just awkward. I could just stand here and then someone's going to open the door and terrify us both because I'll fall on them. And that'd be sad. We don't want to do that. So we're just going to add one thing to this. Before we said whatever energy's in there stays. Non-conservative forces, though, waste a little bit of energy. So let's just say that a non-conservative force is sort of like putting a little hole down there. There's a leak in the bucket. Some of the energy is going to leave. So, that's a leak. This is what the non-conservative force does. This is lost energy. Cause a non-conservative force did work on the system. A non-conservative force came into play and essentially took some of my energy and just got rid of it. So when the problem is done, I'm not going to have as much as what I started with because some of it went somewhere else. Now, by illustrating this as a leak, that points out the idea that like it didn't just vanish. It went somewhere. It's just out of the problem now. It's off doing other things. I don't know what it's doing. It's getting the ground wet. I don't know. It's just not helping the problem. Okay? So we're just going to keep the same equation and add one thing to it. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. And then I need to put a term in to account for the leak. Otherwise, these problems will be the same. That last term is going to go here. And it is the work done by any non-conservative forces. And it will most of the time be friction in our case, because that's the one non-conservative force that we know. You could potentially have conceptual problems where it's like, oh, some energy is lost as something flies through the air. Maybe it's something like air resistance that is acting and leaking away a little bit of my energy. We're going to do 2 examples using this equation. Part of that will serve as a review because, well, the first 4 terms are going to work just like what we did last week. You need to understand how to work in that last term, though. And notice, I said you have to work in the last term. Work the last term. We're going to work. You all just ignore me. You'll laugh later. You'll be like, wow, he's hilarious. That's fantastic. You know, I had another class, and you know what? For some reason, I went off on a tangent talking about, like, my wife and I don't have kids, and we're like, kids, well, I don't know if I can handle kids. Kids sound hard. And then someone, like, literally yelled from the audience, "You're already a dad," because of my jokes. Like, "You're such a dad." And I'm like, get out. Just get out of my class. It's just mean and terrible. And, yeah, not funny, is it? Why did you laugh at that more than... It's not right. I think I should just keep example 3 to myself and then make it the exam problem and never tell you how to work a problem like it. Mm-hmm. Yeah, you're nodding yes, like that's a good idea. Why are you nodding yes? I don't know. So let me draw a problem here. Let's see. Let's say that there is a slope, and it goes down to a flat space. We'll call ground level y equals 0, and we're going to put a box at the top of the slope at rest. Okay, so let's say that this slopey part is frictionless. And then we're going to make the flat part have friction. I need a word for that. The other part's frictionless. What should we call the flat part? Friction more? Frictionful? I like it. I think I'm going to go with frictionful. But less is full aren't really, I don't know. So we'll say that this is frictionful. There. Works for me. And we drew in literally all the little frictionites with their hands in the air, waiting to stop the box. So you can imagine that this box is going to start from rest. I let it go. There's no friction. It's going to go faster and faster and faster and gain velocity as it goes lower. Why? Potential energy gets switched over into kinetic energy until it gets down to the ground level. right? So when I get to this point and I hit the friction, I've got all of this kinetic energy that's gonna get taken away because all the little frictionites are gonna do some work, right? They're gonna be like, yeah, and try to stop the box. And as the box slides across the friction, it's going to take energy away from the kinetic and eventually stop the box, which is what we're going to try to find. We're going to look for this distance or displacement that the box travels before coming to rest on the flat surface. So find delta x. Let me give you some numbers because you like numbers. What if I didn't give you numbers? How would you feel about that? Do you care at all? You want numbers? If you want numbers, I need to know you want numbers. Because we could have this entire class from the start to the end and never have a number. Except maybe, not even constants. We could just use letters the whole time. And there are classes that get taught that way. I know of a particular physics class that is essentially the same as this one. And they just never. Numbers are never given. Everything is symbolic. And everybody hates it. I don't teach it that way, but I could. And maybe I should. Just to break you of your numbers habit. Quit using numbers all the time. I'll give you numbers this time. Mass is 1.2 kilograms. The initial height, I'm going to call it the height at point A as 1.5 meters, and we'll say the coefficient of kinetic friction is 0.57. So instead of using initial and final, I'm going to break this problem up into two parts. So I'm going to give each location a name. I'm going to say that this is point A, and right when it gets to the bottom is point B, and when it stops is point C. So we'll go from A to B, and then from B to C. So what equation are we going to write down? What's the full equation called? No kinematics. What is it? That thing, which is about something, what's it called? What is it, huh? Conservation of energy. Yes, we're writing down an equation that describes conservation of energy. So if I gave you a problem and said, use conservation of energy to solve the problem, you should be able to make that connection and know that we're going to write down this. Except now we're going to put that last term on there as well. In A to B instead of initial and final. Same idea though. By the way, don't forget, a week from Thursday, exam 2. We'll have new material all this week, and it could bleed just a little bit into next week, depending on how this week goes. And maybe we can squeeze in a little bit of a review on Tuesday as well. Again, we'll have to see how today and Thursday go. More than likely, the exam will go through chapter 9, if not just a little bit farther, okay? So, where did we cut things off? Like the second half of 5, 5B, 6, 7, 8, 9, maybe a little bit of 10. Okay, but probably not much at all. So, talk to me here. Is anything 0 in that equation? Yeah, the work that's being done by the non-conservative force between A and B is going to be 0 because we said that was frictionless. Good. Anything else? Remember, it has kinetic energy if it's moving. If it's not, it doesn't. If it's at ground level, it has no potential energy. Yeah?
The kinetic energy at point A.
Kinetic energy at point A is 0. It's not moving.
And potential energy at point B.
And the potential energy when it gets to the ground level down at point B. Anything else?
Explain why they're not.
So for this part of the problem, there's really only gravity that's making it move down. Friction isn't holding it up, so friction's not doing any work. So that one's 0. The potential energy at B, once it gets to y equals 0, I can plug in y equals 0, and that's going to give me 0. And if it's not moving, as when it's at rest at point A, velocity is 0, so that kinetic energy is 0. Okay? And I'm sure some of you are kind of like, well, you canceled 3 things out. Why don't you just keep going and end our pain? We can't do that, sadly. Although, I don't know, it's kind of nice. Should we just sort of work behind that? No! Let's keep going by crossing even more out. Whee! Okay, stop. Just stop. Go back. Just keep going. There we go. I think I got rid of everything. Maybe. There we go. Look at the equation at this point. It's telling us a story. You're like, no, it's not. It's telling us a story. Look at what remains. Potential energy at point A equals the kinetic energy at point B. It's saying that all I had was potential energy, and it all got transformed into kinetic energy. That's basically like the bucket, right? All potential energy went and filled up the kinetic energy. That is what the equation is telling us, and it agrees with what we would understand is happening. So let's take this, and the next step is plug in the equations we have for each little part. We know it's gravitational potential energy, so I'll put in the equation for gravitational potential energy. And we have this one equation for kinetic energy. And then we can solve for how fast it's moving right as it hits the friction. The masses cancel out, that's kind of delightful. And then the velocity at point B is equal to the square root of 2GYA. So the velocity at point B is 2 times 9.8 times 1.5, which is something. Yeah, 5.42. Good. So it went from not moving at all to moving pretty fast once it hits the friction. All of this velocity and the energy associated with it is going to get sapped away and leaked by the friction as it does work, moving from B to C. So let's do the exact same thing over on the right-hand side, except now we're going from B to C. And we're going to start with the exact same equation. Kinetic energy B plus potential energy at B. And by the way, nothing's changed. It's still at point B. We know what both of these are. Equals kinetic energy at point C plus potential energy at point C minus WNC. And a good first step, again, is just think about what's 0. You don't really want to have to write out a bunch of equation stuff only to make it 0 later. If something is 0 because it's not moving or because it's at ground level, let's get rid of it. So what's 0? Kinetic energy at C. I like that. It stops. So that one's gone. And gone. What else? Potential energy at point B. It's at ground level. And I heard something else. Anything else in there 0? Yeah, it never leaves ground level, so that one's 0 as well. And once again, we crossed off 3 of them, so yeah, it's off. No, take it back. It's moving at point B. It has kinetic energy. Where does that kinetic energy go? It goes here. It's equal to the amount of work that friction does as it takes it away. So let's rewrite out our equation. Kinetic energy at B equals negative work done by non-conservative forces, and I happen to know that that force is friction, so I'm going to change the subscript. And then we're going to just plug in equations that we have for each of those things. So the kinetic energy at point B is 1/2 mass times velocity at point B squared. And think back to the last chapter, you know the equation for work. What was it? Delta x cosine theta, and what else? The force, yeah. So it's the friction force, the force that's doing the work, times the displacement, times the cosine of the angle between those two things. So, notice, we've got chapter 8 merging with chapter 7. Ooh, you gotta love that. All happening in the same problem. You're like, no, I hate it. Hate it. Because it sounds like something I'm going to be expected to know how to do. you would be correct. You should hate it. But don't hate it. Just learn it. Embrace it. You know how to do it. Then when you see it on the exam, you'll be like, this is fantastic. I get all these points. I know exactly what to do. What now? What's theta? Delta x points this way. Which way is friction pointing? The opposite way, right? What's that angle? Let's go here. Friction force is pointing this way. So the angle between those two things is 180 degrees, right? They're pointing in opposite directions. 180, okay? What is the cosine of 180? It is -1. So let's go ahead and take that with my two negative signs now and rewrite this again. 1/2 mvb squared equals force friction times delta x. Is there anything here I can substitute in equation-wise? Friction, maybe? Do we have an equation for friction? What was it? I expect you to remember too much. I know. It's terrible. What is the equation for friction? Something. Mu? Mu times what? Mu k here. Oh. Yeah, mu times the normal force. And don't forget that delta x is still hanging around there, so I need to bring that down as well. We're getting closer. Delta x is there. I just need to get something in terms of stuff I know. I know the mass. I know the velocity at point B. I know mu. I still don't know this normal force thing, though. What can I do to find the normal force?
Mass times gravity.
It might be mass times gravity. Are you sure? Is it always mass times gravity? Yeah, let's be careful. It is mass times gravity here, but just to be on the safe side, I'm going to go up here and draw a free body diagram. No, not a free body diagram. It looks something like that. As the box slides from left to right, only the three forces are acting on it: normal, gravity, and the friction force in the negative x direction. So if I were to write out the sum of the forces in the y direction, there is no acceleration in the y direction, so Fn minus Fg equals 0. So Fn is equal to mg in this problem. If there are any additional vertical forces, or if it's not flat, it's going to be something else. So the only safe way to do that is to actually look at the forces and find out what it is. So now I can take that and plug it in down below. Let's do exactly that. So we're going to go down here. Actually, let's take the long way around. Ooh, just because I'm irritating. There we go. We made it. And now some of you are like, where do you go with that? Okay, got it. All right. So let's plug that in. And now I've got 1/2 mvv squared equals mu k mg delta x. And now we can solve this. The m's cancel out, and delta x is going to be equal to vb squared over 2 mu g. And you have all of those numbers. I'll give you a second to play with the numbers and tell me what you get. I feel like you all saved me a seat here. I should just teach from the seat. It's like oddly the only one that color. I think. Why is it a different color? Is it rigged in some way? It's like trying to tantalize me to sit down and lecture just seated. And if I do so, all will be lost. Something will fall from above me. You look suspicious, like you're planning something, aren't you? No?
Watch it just fall apart. That's a little frightening. Okay, I think I'm safe. Does anybody have delta X?
2.62.
6.2, let's see. I like 2.6. We'll just shorten that off. 2.6 meters of horizontal distance before it comes to rest. Thank you. Does anybody have any thoughts or questions or complaints? Basically, 3 different chapters came into play there. The new one, chapter 8, work from chapter 7, free body diagram and forces stuff back from chapter 5 and 6. So maybe even 4 chapters, all in one problem. There's another way you could solve it, a shorter way. I suggest maybe you try it as practice, but let me show you the way to think through that. At the start, there is a certain amount of energy in the problem. It's all potential energy. Okay? As it goes through the problem, that potential energy gets converted to kinetic energy, and then all of that kinetic energy leaks away due to friction. Okay? What if I just skipped the intermediate step and just said that all of the energy I had leaks away due to friction? That's perfectly valid. There's no reason for me to find this. I could say that the kinetic or the potential energy at point A equals all of this stuff at point C, in which that would be 0, that would be 0, and I would just have the friction force. You'll get the exact same answer. So in other words, just as practice, maybe try conservation of energy from A directly to point C, and you get the same result. You're still tracking the energy throughout. I just didn't take the time to find out how much of it went into kinetic energy in the middle. Still works perfectly fine. Okay? Another example? More examples? Unless all of you come up and like physically restrain me, I guess we're doing another example. So, yeah, another example. Something that is similar, but maybe a little bit harder. Let's see. Let's say that we have a slope that looks like this. That's supposed to be straight, but you get the idea. Let's say that ground level is down here. And we're going to start with a box right at the bottom of the incline, and we are going to kick the box, giving it some initial velocity. And let's say the question is, if the box slides 0.52 meters along the incline before stopping, what is the initial velocity? What initial velocity would it take to make it slide 0.52 meters along the incline? I will once again give you some numbers. I will tell you that the mass is 0.55 kilograms. The angle is 24 degrees. We'll say that that is the angle of the incline. And the coefficient of kinetic friction is 0.24. And that's all you get. So we will say that the initial point is down here at the start, and the final point is 0.52 meters away along the incline. At that point, the velocity is 0. Okay? So you might imagine the problem starts just after the kick. The kick is what puts energy into the system, the energy that has to be tracked at that point. So we would put some energy in the system by doing work, by kicking the box, and then we say, ooh, it has some velocity. Let's see what happens after the fact. Okay? So we're going to write conservation of energy from that initial point to that final point. And we will include our term at the end for work that's being done by non-conservative forces, which will be friction once again. And then you're all going to tell me if I can get rid of anything in this equation. With a series of yeses and nos as I point. Can I get rid of it?
No, because it's right after.
Yeah, it's moving. We're actually looking for how fast it's moving there, so that's got to stay around. How about this one?
Yes.
Yes, it's going away because it is at ground level. Yay, bye-bye. How about this one? Yes, because it stops once it gets to that height. Well, what about this one? I got to keep that because it's now got gravitational potential energy and friction is doing work, so I need to keep that one around. So if you take a look at what happens in this equation, all of this kinetic energy I started with is going to go into two places. Some will go into the potential energy that's in the box as it goes up, and some of it leaks away. So this amount is stored, and that other amount leaks. It's lost. Okay? From this point, we're going to follow essentially the same procedure. We always start with this equation and then just go through a series of like plugging in equations that we know for the different things. And I don't know about you, but I kind of like these problems because they just seem like weirdly clean. It's like you're not like getting something from over here and something from over here and doing a bunch of different things. It's like just sort of straight down the line. Just keep plugging things in until you have all the numbers and you can solve for it. Okay? So our equation for kinetic energy is 1/2 mass times velocity initial squared. And then on the right side, we have mgy final minus this work that's being done by friction. We're going to plug in the work equation. It is the friction force times delta x cosine. And I better be careful here because I already am using theta. So I'm going to call that phi. The angle between the direction of the friction force and the displacement. So let me go back up to the diagram. The displacement is pointing this way, that's delta x, and the friction is pointing the opposite way, slowing it down. What is the angle between those two? Once again, looks a whole lot like 180. They're pointing in opposite directions. So this is 180, so that's -1, and then I can rewrite the equation again. 1/2 mv initial squared equals mgy final plus the friction force times delta x. From the previous screen, what is the friction force? Yeah. It's mu times the normal force, and don't forget the delta x. So we'll write the whole equation down again. By the way, be careful with your algebra, especially on an exam. If you're worried about like, oh, I don't want to have to like rewrite things like a billion times, it's worth it to save yourself from mistakes. So I only made one change there. I plugged it in, but then I went ahead and wrote the rest of the line down again. It's a safer way to play. You might think all the way back here, like, oh, I know what the equations are, and I'm going to jump like all the way down here, just trying to substitute all the things in at once and see what happens. Just be careful, okay? Showing me all the steps and all the work, doing one thing at a time in each step is a little bit of a safer way to get to answers. So, what is the normal force? Or do I know yet? Yeah, I don't know without doing the free body diagram. So let's quickly do that. Normal force is that way, gravitational force is down, and the friction force is backwards along the incline. I'm going to say that that is positive y and this is positive x. And in order to get something for the normal force, I'm going to have to break up gravity into components. It's the only way we can get there. So we're going to have a component that direction and a component this direction. That is the angle of incline. This side is going to be FG sine theta. That side is FG cosine theta. And yes, free body diagrams have become just a little side thing. It should be so second nature at this point. How many of you have been looking around the world seeing free body diagrams around you? How many of you have dreamed of a free body diagram? You can admit it. This is a safe place for this. You know, it's okay. Because it happens, especially when you're spending a lot of time on homework. Like eventually you're just like driving down the street and you're like, you see a traffic light and you're like, oh, tension forces, gravitational force, like all of a sudden, like it's just there in the world around you. Or you're just like, there's a chair. I see a normal force and a gravitational force. Like stuff just happens. And then you close your eyes at night and you're like everything in this dream has a free body diagram. What's happening? And then you wake up with cold sweats and everything is just terrible. You know, it just, when you're immersed in something, it's going to happen. And you can admit that without any ridicule. It's fine. I used to play Pac-Man a lot. Anybody? Pac-Man's the best. Even today, Pac-Man is fantastic. And I would play so much that like when I would close my eyes, I would see like ghost patterns, you know, going different directions and imagine myself getting out of different ways. It just, same thing with Minesweeper. Back in the, is it even still on Windows machines?
Yes.
Yeah. I used to play a lot of Minesweeper too. I'm a sad individual. Pac-Man and Minesweeper. And Tetris. Lots of Tetris. Yeah. Anyway, you're all thinking like, why don't you play like Fortnite or something? Sorry. The simple games are amusing for some reason. The simple classics. Let's see. So in the y direction, that acceleration is 0, so I have normal force minus Fg cosine theta equals 0. So the normal force here is equal to mg cosine theta. So it is different this time because we're on a slope. The equation for the normal force comes out different. But I can now plug that in and I should have everything I need finally to solve for V initial. So let's write it down one more time. 1/2 mv initial squared equals mg y final plus mu k mg cosine theta delta x. Ugh. And the m's are going to cancel out, and we can rearrange that to solve for V initial, and then life will be happy. By the way, you can't play Pac-Man on a touchscreen. It saddens me. Like if you're really going to play some Pac-Man, like you need the arcade, you need the full joystick, because like things get serious, things get dangerous. Like you need to be able to make split-second maneuvers, and the only way to do that is to literally practically break the joystick at some point. Like that joystick should not be the same as the way you found it. You need to leave the joystick in a different state, because, you know, like, ugh. See, Pac-Man, back when it was just a quarter, actually still, if you can find an arcade, like they're not going to charge you more than a quarter to play a game of Pac-Man, I can go a good half hour on that quarter. That is money well spent, you know? A quarter, a half hour, like you spend $1, you got 2 hours of fun. Just can't go wrong with that. What are we doing here? I don't even know. I just want to play Pac-Man now. And just like swiping to change directions, like you just can't maneuver as quickly. Like 2 swipes to like 2 quick. No, it doesn't work. Makes me sad because I've wanted a happy Pac-Man game. It's just not doing it for me. Solve that for V initial, please. Multiply by 2 and take a square root, essentially. So V initial is going to be the square root of 2 times g y final plus 2 times mu g cosine theta delta x. And we have all of that stuff. Or do we? Question.
What happened to the 1/2?
1/2, I multiplied everything by 2.
Oh, okay.
So then I get 2's on the other side. Yes.
Were we told Wi-Fi?
We were not, but I think we can find it. Let me go back up to the top real quick. Y final is this distance And we know the angle and the hypotenuse. So the sine of 24 is going to be y final over 0.52. That is hard to see, but I was wanting to use a different color. So y final, I think, is 0.21. Just using the trig and the geometry of the situation as it sets up. So now, should have everything you need. The initial, I've got about 2.5 meters per second, result in it sliding up the incline that particular distance. Conservation of energy with work and forces makes for a really good exam problem. It turns out, as we're going to see in the next chapter, I can even make this particular problem include the next chapter as well, which is kind of fantastic. I should just give you an exam with one problem. Like you just start at the beginning of this and it just takes you through all the chapters. It's like a story in exam form. And then some of you would love it and others of you would be like, oh, I don't want to do that problem. And then all will be lost. You get hundreds and zeros. Would it make grading easy? Binary grading. I like it. Zeros and ones. Question.
How many points would this problem be worth?
How many points would that kind of problem be worth? Probably 30. Yeah. About a third of the test could be something like this. Prepare yourself now. So now if you're thinking like, oh, dang it, I slept through the last two slides. Oh, all is really lost. Go back and review these two slides. There are an infinite number of varieties on this basic theme that I could pull out and
So
give you a
for
problem.
sure that's going to be on the test.
Something conservation of energy with friction will be on the test. Yeah. No way to avoid it. So you will notice if you've looked at the slides, there's quite a few left in this chapter. We're not going to do most of them. Yay, right? That's kind of nice. There's like 2, maybe 3 of these multiple choice questions. And then after that, once you get sort of to the end here, all of this stuff is sort of like bonus material. You don't need to know it, and we don't actually need to cover it. I generally like to talk about it if I have time, but since the semester is running short, we have 9 lectures after today. Does that sound right?
Are we not going to need it for 2:30?
No, not really. There's some stuff in there where it's kind of like, oh, I've seen that before, but it's having it or not having it won't really help or hurt. So, yeah, you're welcome. Or something. So instead, what we're going to do, we're going to get rid of that one as well. We are going to do this one. We're not going to do that one. We are going to do that one. We are going to do that one. We're not going to do this one. There we go. Beautiful. Now you're like, which ones did he cross out? Like, I don't know. Instead, we're going to take these 2 problems and talk about Paul and Kathleen. Any Paul and Kathleen here? If so, you're probably not going to volunteer that information at this point. Paul and Kathleen start from rest at the same time on a frictionless water slide. 2 different water slides with different shapes. Which one has the greater velocity at the bottom of the water slide? This is kind of a repeat from earlier. Both of them have to be the same. They start with the same potential energy. So we'll write this down. Same potential energy and kinetic energy equal to 0. And that means they have to end with the same final kinetic energy. All of that gets converted over into kinetic energy. Okay? So they're starting at the same height. The path doesn't matter. So what if the paths look like that? First of all, these people are having all kinds of fun. More fun than they should be on a water slide that looks like that. And just look at Paul. Paul's face is mush. He's having so much fun. It's just gone. So, and I think, he might have even lost a finger. That could be 2 fingers side by side in the middle, but it's really hard to tell. How's Kathleen doing? We can't see her face. Can't really see her hands at all either. Everything's a blur. They must be moving terribly fast. I don't know what's happening. So, notice it asks who makes it to the bottom first. Any thoughts? No thoughts. Still thinking. No out thoughts. What do you think?
At the same time.
Same time? Same time? Same time? Not same time? Same time. I like that answer because that would be exactly what I would say at first as well. Kathleen? Paul. Wow. So it's one of these three answers. We have determined that as a group. Good job. Let's start here. They both start at this exact same point. What can you tell me about their potential energy at that point? Same. Same potential energy. And kinetic energy there is equal to 0. What can you tell me about their potential energy down here? It's the same potential and the same kinetic energy. We've already determined at the bottom that V final will be the same for both of them. Okay? Maybe that still doesn't help us answer the question. I don't know. What can you tell me if we were to look at when Paul is right here compared to when Kathleen is right there?
Kathleen is going faster.
Yeah, Kathleen there's moving faster, right? Because Paul still has almost all of his potential energy, but Kathleen's lost a little bit, which means she's gained some kinetic energy and some velocity. So at this point, Kathleen's moving faster. Okay? What about if I compared, say, this point to this point? Same thing, right? Kathleen is lower, closer to the ground, which means more kinetic energy. So at that point, Kathleen is faster. In fact, notice every point on the two curves. They start at the same point, but everywhere else, Kathleen's curve is lower than Paul's until we get really close to the end. That means at all of these points, she's traveling faster. If that's true, she has to get to the bottom sooner. It's the only possibility. At every point along there, except for the beginning and the end, she's moving faster, which means Kathleen gets there first. If that bothers you, let me explain that whoever made this diagram put something in that's deceptive. It's never, ever, ever at any instant in time going to look like this, where Kathleen is directly below Paul on the two slides. That can't happen. Why? Well, even like right here, if Paul's barely moving, but Kathleen's moving faster, this isn't even going to happen. Kathleen would be here, but Paul would still be lagging behind. Okay? When we get to this point, when Kathleen's here, Paul's probably still back there somewhere. So it looks a little bit more like this, like she kind of takes off, and then Paul's like lagging behind. So she gets there first, and then Paul comes in behind. But if you were to just look at this point and watch them go by, they go by at the same rate, the same final velocity. They just don't get there at the same time. Yeah, this one tends to be a confusing problem for a lot of people. So I'm going to take 2 breaths and see if you have a question. Okay, I want to move on. Yeah, I know. Scared you, didn't I? Anybody? Okay, think about that one some more. If it still bothers you, ask me questions. Let's head over to this one, and this will be the last slide of this chapter, which will give me enough time to introduce the next chapter before we dig into it on Thursday. I'll just tell you the key lies, well, right there in those italicized words. Any thoughts that you'd like to share verbally? Yeah.
If it's at a constant speed, does that mean that the kinetic energies are the same from initial to final?
It does. If they're moving at a constant speed, the kinetic energy is not changing.
2.
2, 1. I heard 2 and 1. Nobody likes 3 or 4? 2 or 1? So which one? 1? Or is it 2? 1, 2. If it's not speeding up, so we've determined the kinetic energy is not changing as it falls. What's the potential energy doing as it falls? It's decreasing, right? Where's that energy going? It's not going into kinetic energy. It must be going into like friction or something, maybe air resistance, okay? So it is a leaf moving at constant speed. You can kind of imagine this happening, right? Maybe it does this on the way down, kind of a thing, all right? So what's happening is it's losing potential energy, but the kinetic energy is staying exactly the same the entire time. Sounds to me like I don't have as much energy at the end as what I started with, because some of it went away. If I don't have as much at the end as what I started with, then it looks like I had more at the beginning. So in other words, we have some lost energy from air resistance, which is really just another form of friction. It's the same kind of idea. Okay? And we're done with chapter 8, unless you have questions. No? Chapter 9. Okay? Chapter 9 is going to finally allow us to do something that we've been avoiding. You're like, what, physics? No. A part of physics that we've been avoiding. What, homework? Stop talking back. That's all there is. Like, what, you're talking back. Yes, okay, now I'm having a conversation with myself. I'm going to stop all of this. We've been avoiding things sort of hitting other things, right? When we like tossed a ball into the air, we said, okay, find out how fast it's moving just before it hits the ground. We just completely ignored that part where it actually slams into the ground. When we had, maybe even we're throwing the ball, we said, like, get rid of that part where you're throwing it and look at just after you release it. So when things are sort of coming into contact with each other, we've been cropping off those parts of the problem because we didn't have the tools to solve it yet. At this point, we're going to bring them in. We're going to bring them in the term here, collisions. Collisions could be considered sort of forwards or backwards. It could be when one object runs into another, or maybe the objects start together but then separate. That would be kind of an inverse collision. That would maybe like when I kick an object is when I kick the object and then it goes somewhere else, they slam into each other, versus when I throw an object, maybe I have the object and then we come apart, okay? Objects touching other objects in some way or another is what we're going to be dealing with. And the tool that we use is momentum. So just put those two things in your head together. Momentum collisions, momentum collisions, momentum collisions, momentum collisions, momentum collisions, momentum collisions, momentum collisions. They're always going to work together. Your tool for solving collisions is momentum. So first we need to talk a little bit about momentum, and we're going to have several slides we do with that. We're going to cover this slide, and that's going to be it for today. That's about all I'll have time to do. Just to stay on track with the other class, we might have ended up faster than the other class. It always goes the other way around. We'll see how the slide goes. And then later on, once we understand momentum, we'll be able to deal with the collisions themselves. So first of all, we're dealing at this point with linear momentum, which is something we're just going to call momentum. The only reason I need to make that distinction is because later we're going to have angular momentum, which is another type. So if I say momentum, what I really mean is linear momentum. And even though this isn't the best definition, I think it's enough to get across the idea of what we mean by momentum. Notice we're saying it's equal to the effort needed to stop an object. It's equal to the effort needed to stop an object. We would say an object has a certain momentum, and it's equal to how much effort it would take to stop it. So if you imagine that for whatever reason, I am just walking across the front of the classroom. So I'm heading toward that door. I'm walking like this. And one of you just freaks out. You're like, I think he's going to leave. I think he's going to walk out the door. I don't want him to walk out the door. I don't understand the physics yet. I want him to keep explaining the physics so I don't fail the exam. This is opposite of what you're probably thinking. You're probably thinking, leave, see if I care. So you jump up from the back of the classroom and you're like, I'm going to stop him. I need to stop him. How much effort is it going to take? Well, he's not moving terribly fast. And you look at me and you're like, he's not that big. Like maybe a little big, but not that big. So you're like, I think I'll just go, and he will stop. Not a lot of effort. Notice, it involves my mass, it involves my velocity. Because if we switch that around and all of a sudden I'm like, I can't take this class anymore, I'm sick of all you people and I'm leaving. And I just start sprinting to the door like, yeah! And one of you's like, I need to stop him! But wait a minute, he's running. That looks difficult. It's gonna take more effort. Maybe I'm not gonna bother. Let him go, okay? More velocity, more effort required. On the other hand, what if we come back to this classroom 30 years from now and I've eaten 30,000 additional donuts from my current total, which I don't know what that is. So now it's all of a sudden like, maybe I'm just moving this fast toward the door, but now it's like, ah, because I'm literally this big, okay? And like things are like shaking over here as I walk by, and now you're thinking, he's not moving very fast, but alas, his mass is a bit large. It might take a lot of effort. I'm going to pass, okay? Mass and velocity are involved. If you watch a lot of sports, you hear this word thrown around a lot, right? It's like Team A is doing well. They seem to be destroying Team B. They might say, Team A has all the momentum. This is fantastic. They have all the momentum. And then somebody falls down, drops the ball, the other team gets it, right? And now they're like, Team B has all the momentum. And it's like momentum's going back and forth. Really, they're using that definition, right? They're saying like, this team is hard to stop right now. They have momentum. It's difficult to stop them. Not necessarily because of their mass and velocity, but the idea holds up, okay? So we've talked about mass and velocity being involved. Velocity is a vector. It turns out that is the equation for momentum. It's just mass times velocity. If either one is larger, it's going to take more effort to stop that object. We'd say that it has more momentum. Notice I've left off the left-hand side of this equation because this is one of those cases where the letter we get to use doesn't seem to make a whole lot of sense. I can't use M for momentum because it's already there. So instead, we're going to do what seems like drawing a letter out of a hat and use P, which I know is a little sad and makes it hard to remember. P is the symbol we'll use for momentum. It is a vector because velocity is a vector. And maybe it would help you remember that P stands for momentum if I tell you a little bit more about why we use P. Would it be useful? You're like, no, just walk out the door. You're already next to it. Why are you people so mean today? I don't really understand what's happening. So if you were to go to the library after class today, go to the physics section and be like, give me the oldest physics books you have. And then we'll look at those. And then you look at them and you're like, 1968. Not old enough. I need older. And then you get something from the 1800s, which they don't have, probably. So you go to a different library. You're like, older! I need something from the 1700s. And you keep working your way back until you're like, oh, physics scrolls, right? Like, I don't know that this exists at all. But find some old physics writings, and you'll find that the spelling of momentum has changed over the years. It used to be spelled like this. Kind of like pneumonia with a silent P, or pterodactyl, or pneumatic, or something. It used to be spelled momentum, which is what we're going to call it most of the time, just because I kind of like that. Momentum. I'm also the same person that if someone's like, like, I got pneumonia, I'd be like, oh, you got the pneumonia? Because I'm just mean and irritating that way. Also, this is a lie. So let's just completely get rid of that. Yes, Total lie, but now you'll remember momentum, and then we use P. Yes, I'm allowed to lie. The teacher lies. Too bad. At least I told you I lied. So don't go to the library looking for any old physics scrolls, because no. So let's see, what else can we do with this? This is in units of kilograms and velocities meters per second. And we have no fancy unit, instead it's just kilogram meters per second is the unit for momentum. And to help illustrate the vector nature of momentum and also just sort of how problems like this work, we are going to work a quick example that fits right in the middle of the screen there. Looking at two different objects falling to the floor and colliding with the floor, okay? Notice, we are going to try to find the change in momentum, so we're going to be looking for delta P while the object is hitting the floor. If you're thinking like, I can do a problem like while it's happened, like it's almost hitting the floor and then it hits the floor and it's over. Like, that doesn't take any time at all. How can I do a problem while it's hitting the floor? Well, it takes a little bit of time, which is not very much, right? It's a tiny little slice of time. You might imagine if I drop something, it's falling, 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 it hasn't quite hit this yet, it still hasn't quite hit it, it hasn't quite hit it, but it's about to. That's where the problem begins. That's the initial point. And then it moves a little more, it hit it. That's the final point. Like literally, it's a tiny little slice in space and in time that we're going to do the problem with that. So it's literally from just before it hits the floor to just after it hits the floor, which makes our diagrams a little hard to draw. But let me show you what I mean. Part one, or rather problem number one. We're going to say that we have a bean bag, a bag of beans that we're going to drop to the floor. When they hit the floor, what do? Basically, they just stay there. Splat, right? Might be the way to describe it. So if I drop them, they're going to gain velocity, gain velocity, gain velocity. They're going to have velocity and then not. Okay? So let's say here's the floor, and here is the bean bag of some odd shape. That's, look at that. Oh, I didn't leave a gap in there. Now we got to fix that. I just ruined it all. That's just terrible now. See? I did it again. That, yeah, there we go. There's a gap. It hasn't quite touched the floor yet. That is the initial position. How do you like that? And we're going to say that at this point, it has a velocity initial downward. Let's also say that up is the positive y direction, so that that's a negative initial velocity. The final position is here. Look, now it's touched the ground. See? Major difference, right? Not much has happened there. And at that point, it has no velocity. That is our final velocity. So if I wanted to find the change in momentum, delta P, that's equal to P final minus P initial. And there's a reason we're doing this change in momentum instead of just finding momentum, as we'll see on Thursday. And then we can plug in the equation for momentum for both of those. So that's going to be mv final minus mv initial. And we know that the final velocity is 0, so the change in momentum is negative m times negative v initial. Because it's going down, it's a vector, I have to include that direction information. So that means my change is positive mv initial. And if that positive sign bothers you, let me describe it this way. Sort of like using a number line. Let's say that this is 0. Over here's the momentum we started with, which was minus mv initial. It changed from this value up to this value. It had this, now it has 0. That change is a positive mv initial. Agreed? Yeah, perhaps, maybe, okay? That was my initial value, this is my final value. We changed from that negative to that positive, that amount. To end today, let's do one other thing. Let's say we have a bouncy ball The bouncy ball, we're going to say, is so bouncy that if I just drop it from a height, it basically comes all the way back to my hand. It's an extremely bouncy ball, right? So that when it hits the floor, that would mean it rebounds with basically the same velocity. Velocity initial and velocity final are the same, just in opposite directions. So if we were to draw a diagram for that, we could say that right there, whoops, wrong way, is V initial, and then V final is just going the opposite direction. We're going to say that V initial equals V final, except for the sign. So I should put magnitude bars around that. V initial down is negative, V final is positive and upward. So that if I solve for the change in momentum, that's mv final minus mv initial. And then let's just make both of those v's, if that's okay, and plug in the sign that they have. So v final is in the positive direction, so I'm going to leave that as positive. And v initial is in the negative direction. So that's 2 times mv is my change in momentum. There's more change in momentum for the second part. We'll see why next time. But if you're bothered by that positive 2 mv really quickly, we started with minus mv and we went all the way over to positive mv, skipping 0. That total change is 2 mv. Okay? And we are done for today. We'll pick this up on Thursday and probably finish this chapter on Thursday if all goes well. All right? I'll see you. Go vote. Go register and then go vote, please. Now, bye. Skip your classes. Go vote.
Did you register when you moved this year?
Did I register when I moved here?
Yes.
Yes. About a month ago. But you can register today.
I already voted. I have the vote by mail.
Perfect. Fantastic. The rest of you go vote. Now.
Yeah, no, I wanted to vote for it. I didn't register. No, I registered. I am registered. I just got my ballot.
I sent you an email